Welcome back. We're going to be continuing now. We voted earlier to take it out of order, so now it's the town's special permit application number 6215. Attorney Tillotson.
Thanks very much, Diane Tillotson. I keep going to this microphone as if it's going to do something in terms of amplification. I realize it's not. Diane Tillotson, representing the town of Falmouth. I'm going to just give a very brief introduction. As I mentioned earlier, even though this special permit application is for only Route 1, we are hopeful that through our presentation, through the board's questions, it will become, or a series of conditions will become evident that will allow Wind 1 to operate, and we contemplate that those conditions could well also include Wind 2. And our next witness is Christopher Menge from HMMH. He is an acoustic engineer. He's been an acoustic engineer for over 40 years, and for the past 10 years has been involved in the specific acoustic engineering for wind turbines in New England. And again, I've just given all of you a copy of Chris's impressive CV. I would ask that as you listen to witnesses, you take into account, as would a court, the qualifications of the various witnesses. Chris's study was both for the existing impacts for Wind 1, and he also modeled the anticipated sound impacts for Wind 2. So he clearly took into account both Wind 1 and Wind 2 in his analysis, and you'll hear testimony with respect to both Wind 1 and Wind 2. I've provided each of you with a actual physical hard copy of his presentation, his slide PowerPoint presentation, which is under tab A, so that in the event you wanted to scribble some notes or had questions you wanted to ask, you could do that. And then B is a document that I've submitted before. I'm giving another copy to the board. It is the sound, the sound study that was done back in 2010, and the PowerPoint presentation is largely taken from this sound study. So without any further delay, I'd now like to call Chris to the, I want to say, to the stand, to the podium, to do his presentation. Thank you.
Thank you, Diane. Evening, members of the board, Chairman. Well, I was asked to not only cover my own study that we conducted back in 2010 and a little follow-up that we did after that, but also studies that preceded and succeeded the studies that I conducted. you sort of the big picture. So this is a little brief outline on my company and me. My company was founded in 1981. I joined them in 1983. My founders and I all worked together at BBN, Bolt, Brannick and Newman, which at the time we joined was the largest acoustical consulting company in the world. We were kind of a spin-off, and we focused on community noise, primarily transportation noise. We have 4 offices now, about 40 staff, and we have a noise and vibration focus. That's pretty much what we do. As Diane said, I'm an old guy. I've been doing this since 1972. And in the process, all these years, I've developed a national reputation for expertise in highway noise analysis, outdoor sound propagation, noise barriers. I've given presentations worldwide, developed the acoustical algorithms for the Federal Highway Administration's traffic noise model, which is required for use nationwide on all highway construction projects with any federal funds. I was a vice president and member of the board of directors for our professional organization, the Institute of Noise Control Engineering, or INS. And as Diane mentioned also, I've done a number of wind turbine noise study projects. Diane thought, and I agreed, that a basic introduction to sound, what is sound, might help. It's going to, I think, help you understand many of the descriptors and metrics, the terminology that we use. To the extent that you may be baffled by some of them, I hope to, in maybe five minutes here, help you get a better picture on what all these terms are and what they mean. Sound is basically anything we can hear. That's how it's defined. And what it results from is variations in air pressure, or water, or other elastic media. That's also called sound. But you think of air pressure, barometric pressure, that changes very slowly. We can't hear that. Pressure pulse from a car door slam, you can hear that, but that's normally not called sound inside the car. But if it occurs 20 times a second, if the pressure fluctuates or more, that often can be detected and can be called sound. Some of the aspects of sound that we can quantify, we can measure its speed, we can measure its frequency, we know what wavelengths are, sound are a form of waves, and we can determine loudness. Let's talk a little bit about what sound really is. Here's a depiction of sound, a piston or a speaker vibrating inside this tube, and this vibration creates a traveling wave of air pressure pulses. And what we have are these sections where the air pressure is higher, where it's compressed, and then we have sections shown with the lines more separated where the air is rarefied, where the pressure is reduced. This reflects a steady sound, like a pure tone, a single tone. So that's why we see nice regular intervals here. The wavelength is defined as the distance or the length between peaks, and the wavelength and the frequency are related because the frequency is the rate at which the number per second of these compressions that pass a single point in time. Now, the compression, the density of these lines is a way to think about the amplitude or the loudness of the sound. So if they're very compressed, then that's a louder sound. If they're only slightly compressed, it's not so loud. And this picture above is another way of depicting sound amplitude, but with the sine wave. And this would be the ambient air pressure, and the rise and fall above that ambient air pressure would be the volume or the amplitude, how far it goes. Again, the wavelength is the distance between these peaks. Now, we humans can hear a lot of characteristics of sound. We can hear different loudness, we can hear different frequencies, and this is a graph to try to help you understand human hearing and how, the range of loudness and the range of frequencies we can hear. This is a set of equal loudness contours, and what it shows is the On the bottom scale is frequency. On the left are the lowest frequencies we can hear, and on the right are the highest. And this shows you a piano keyboard on the bottom for reference for the fundamental frequencies of the piano. The middle C here is at about 260 hertz. Hertz is another term that we use for cycles per second, or the number of those compressions that pass by per second. The vertical scale here is in decibels over on the right. That's the a logarithmic metric that we use to describe sound. It's a little bit like the Richter scale for earthquakes. For earthquake vibration only, it's 10 times the Richter scale numbers. So I'll step back. And the increasing loudness is shown from 0 up here to which is the lowest sounds we can hear, up to very high levels of sound. Notice that the dashed line at the bottom here is indicated as the threshold of hearing. And this is really the quietest sounds that we're able to hear. Notice that the ear is very sensitive and goes below the 0 decibel range here in the higher frequencies of about 2,000 to about 7,000 hertz. This is the baby crying frequency. We humans are very sensitive in that range, I think for good reason. And down here in the lower frequencies, like 20 hertz, the sensitivity is much lower. It takes a sound level of about 60 decibels to hear it at a very low frequency. And that frequency might be the deepest kind of rumble of thunder that you could hear. This next slide is the same family of curves, but I'm showing you what the curves individually mean. If we look at this 1,000 hertz, which is a middle frequency tone, and we go up to see where it meets the 40 curve, we see that at a sound pressure level of 40 decibels is where it intersects the equal loudness curve of 40. But if we look at, let's say, a low frequency of 50 hertz, up here we see that the curve intersects the 40 at a 65 decibel range, which means that a sound pressure level at 50 hertz needs to be about 65 decibels for it to sound as loud as a sound at 40 decibels at 1,000 hertz. And these curves support the reason for why we use weighted sound levels when we talk about noise and its effect on people, because the A-weighted sound level, the A-weighting network, pretty much reflects the human hearing at this sound level, where our hearing is not as sensitive at the lower frequencies. Also, it's good to point out that the A-weighted decibels that we use for noise have been shown in many studies to correlate best with human perception of noisiness. This is my noise thermometer that is included in my report, as well as here in this slide. And it shows the common outdoor and indoor sound levels in dBA, A-weighted decibels. And I'll just show you here that in the range of from about 25 to about 40 decibels, we're looking at the background sound levels of nighttime from quiet rural areas to quiet urban areas. Now, we also use metrics to describe how sound changes with time, or what is the characteristic of sound over time. And if we think about just perhaps the A-weighted sound level, which is the aggregate of all sounds, this is a depiction of how the sound might vary over a period of about 100 seconds at some microphone that you might conduct a measurement. And we have a range from about 35 to 55 decibels here on the left, dBA, and we see that the sound level varies along here from up and down throughout this period of time. Now, we have certain metrics that we use to describe the A-weighted sound level over this period of time. The highest sound level that's reached is around 54 decibels. We would call that the L max. The L stands for level, because sound levels in decibels are always called levels. The minimum sound level that we see here is about 37 38 decibels. We call that the L-min. And then notice that there's one here called the L90. This is the line that comes across. This sound level is about 39 to 40 decibels. This is the sound level that is exceeded 90% of the time. So if you think about how that sound varied throughout that whole 100 seconds, the quietest it got was about 37.5, but the L90 was about 39.5, and it got all the way up to the L max of 54. 90% of the time it was above this L90, and 10% of the time it was below. This is a commonly used sound metric, the L90, to characterize background sound levels, or the quietest periods of time, during a measurement period. And we'll be talking a lot about L90s. There's also this one in the middle called the L50. That's the median sound level. It's louder than that 50% of the time, and it's quieter than that 50% of the time. That's used sometimes. And then another one called the LEQ, and that's the equivalent sound level, or the energy average sound level. And that really is a value that represents the same amount of sound energy as the total energy that is occurring by the fluctuating sound throughout that period. So the energy average sound level for that period is about 46 decibels. So that's a quick introduction to sound and sound metrics. And so we will now jump into a discussion of some of the noise studies that have been done over the period of time from the beginning of this process with regard to Wind 1 and Wind 2. This is a brief outline of what I will be talking about, the studies that I'll be talking about. In 2005, the KEMA feasibility study. Then there was a study in 2008 with Epsilon conducted for the Notice Clean Energy Turbine, and that has a special application to what we did in our study, so I'll mention that. Then, as you've heard, the Wind 1 turbine was started operation in March, April of 2010, and we started we were contracted to do a study of not only the existing sound levels and of Wind 1, but also a projection to what would it be with Wind 2 operating as well in the future, given the concerns over sound from Wind 1. So we started that study in May. It was scoped in May, and we started it in June 2010. Also, Noise Control Engineering, or NCE, represented most of the time by Michael Batarian. Also did some acoustical measurements of Wind 1 during the period that we conducted our study. In 2012, Massachusetts Department of Environmental Protection did some additional measurements, some compliance measurements. They had some concerns about the approach that we took in our study, and did their own measurements, and I'll be talking quite a bit about that later. And then in 2015, NCE did some infrasound measurements, which I've received a report on, and I imagine you have too by now, that I will address as well briefly at the end. So, going through the studies that preceded my study, the KEMA study, a quick summary here: it predicted a potential of 42 to 44 decibels maximum sound levels at the nearest homes. At that time, they were considering the possibility of a single GE 1.5 or 2.5 megawatt turbine. They did not expect that to be a significant noise impact due to various factors, relatively low sound levels, terrain, foliage, and existing background noise. I will say that back at that time, noise issues with regard to wind turbines were relatively unknown, because wind turbines were fairly new in the environment, and we acoustical professionals have become accustomed to sound impact, noise impact criteria in the 60s, in the 60 decibel range from transportation sources, for example, Federal Highway Administration, Federal Aviation Administration. A noise impact is 65 decibels, average sound level, that kind of thing. So when complaints started coming in at sound levels, significantly below that, it was a little bit of a surprise. and it was the 42 to 44 was not thought to be, at that time, to be a potential for noise impact. In 2008, Epsilon Associates did a sound impact assessment for the Notice Clean Energy turbine, and one of the things that I took from that study was data from some ambient background measurements that they conducted at a wide range of wind speeds, and including some higher speeds that occurred during their measurement program in Falmouth, in this neighborhood, that occurred during our measurements, and we used those to our advantage in our study, and I'll address that more later. Okay, so at the very outset of my study, it became a collaborative process where we worked with the town, and we worked with the town's consultant, noise control engineering, Michael Batarian in particular, to review the scope of work, what our study would include, all the elements that would be in it, and they signed off on the approach that we came up with for the study. The study involved long-term continuous sound level and wind speed measurements conducted with Wind 1, periodically operating and then shut down. And we chose this period because it was a maintenance period where they were planning to shut it down for intervals of 12 hours, 24 hours throughout this maintenance period. And that way we would have these nice periods of shutdown and operation where we could do comparisons between the measured sound levels. We also conducted some short-term attended measurements at 4 community locations. We conducted some reference measurements at near the base of Wind 1, and then modeling, as we've talked about, of noise from Wind 1 and the yet-to-be constructed Wind 2 to determine this combined effect and what would that be. And then also we were predicting compliance with Mass Department of Environmental Protection policy as well. Well, initially I will just mention the standards that we were looking at. The Massachusetts Department of Environmental Protection has a noise policy, and their policy states that sources of sound should not increase broadband sound levels by more than 10 decibels above the ambient, and that's A-weighted sound levels. And they define the ambient as the L90 without the turbine operating, in other words, or the background. Also, sources of sound should not create what's called a pure tone condition, which would be tonal sound, hum, screech, a tone of any kind. And that is defined in their policy is that such that one octave band of sound cannot exceed an adjacent band by 3 decibels or more. And when I talk about octave bands, we'll show you some octave bands and some 1/3 octave bands a little bit later. But what I'm talking about is breaking the sound up into different frequencies. So what we do is to analyze sound, we break it up into different frequency bands, and each one might be an octave on the piano. In each one of those bands would be a way for us to evaluate the low frequency component of sound versus the middle and the high frequency component by individual octave bands. And then the town of Falmouth has its windmill bylaw that says that there shall be a rebuttable presumption that noise from the windmill in excess of 40 dBA as measured at the property line shall be excessive. So we address that as well. Well, what I've done with this presentation here is I have taken a presentation that I already made to the town back in 2010 in September as a result of my study. And I have added a few things. But a lot of these slides that you're going to see come right from the report, come right from graphs and some tables in the report. And so I'm basically providing an overview of the report, although I add some more detail in this. Diane and I thought it would be useful to really give you a full understanding of it in case you haven't had the opportunity to really sit down and read it. We realize it's dense and long, so we hope that this helps you out. So at the beginning of that presentation, I provided this list of key findings to sort of set the stage so that you can be thinking about how things played out in the study. One key finding was we found that the background sound levels increase with wind speed. We found that sound from wind 1 by itself did not cause violations of Mass DEP noise guidelines, but they approach the 10 dBA increase threshold on Blacksmith Shop Road. We found that both wind 1 and wind 2 operating with our modeling predicted no violations at any of our measurement positions, but slightly greater than a 10 decibel increase at a couple of locations at the end of Ambleside Drive. And that would be during the early morning hours when the background is quietest and with wind speeds in a fairly low speed range of 5 to 6 meters per second at the turbine hub. The nighttime background sound levels with low wind speed measured in June by us are nearly the same as those measured in January in 2008 by Epsilon in the same general neighborhood but not in the same locations, which suggests minimal seasonal variation. It's probably worth pointing out to you that these June measurements that we conducted were conducted, and when I talk about nighttime background, I'm talking about times in the middle of the night, the very quietest periods of the night, and we did not have insect sound or peeper sound in June, and so it was very quiet during those periods. Finally, a key finding was that our reference measurements suggested that the Wind 1 turbine is operating at or below the manufacturer's specifications. That was a question that came up. Is this thing even within spec? Is it defective or something? So they asked us to do some reference measurements close in. So we did our best to do that. To do them properly is actually quite difficult and complicated, and actually would have required me to move the turbine, which wasn't an option. So we did our best, and I think got some good conclusions, and we'll address those. So let's get into the measurement program quickly here. We had 2 long-term measurement sites for the 10-day period where we set up noise monitors to do continuous monitoring. One was at Neil Anderson's house at 211 Blacksmith Shop Road. We call that LT1 in the report. And LT2 is for long-term 2 at 124 Ambleside Drive, which is over on the other side of Route 28, near where Wind 2 would be opposite where Wind 2 would be constructed in that area. We conducted continuous monitoring of the sound level every second, and plus looking at 10-minute interval summaries. And we collected not only the overall A-weighted sound level every second, but we also got the 1/3 octave band spectrum every second to give us a really good understanding of all the frequencies at all times. We also conducted periodic recordings. Our instrument has the ability to, just like your phone does, or a high-quality recorder does, you can make an audio recording with it. And so our instrument did that as well. So we have recordings that we can listen to after the fact. Simultaneously, wind speed monitoring was conducted. Not only at the noise meter, we had our own ultrasonic anemometer positioned at the noise meter. There are some photographs in the back of my report of some of our noise monitoring locations, and you can see pictures of our instruments and the funny-looking thing that looks a bit like a claw is a ultrasonic anemometer, which has little sensors, and it determines what direction and what speed the wind is going between these little sensors on either side. So it's very quiet; it just sits there. And so we measured it at the noise meter. We also measured it at the turbine hub with the turbines, anemometers, and also at a 10-meter met tower that was on site. We also conducted some measurements at 4 different short-term sites. And for there, we got 30-minute intervals on 4 different days and times, 10-minute intervals, summaries, continuous A-level and 1/3 octave band, and wave file recordings there too. The sites are shown here in this picture. We have LT1 down here at 211 Blacksmith Shop, up here LT2, Ambleside Drive, and the addresses for the other measurements are ST1 is at 161 Blacksmith Shop Road. ST2 is at 27 Ridgeview Street. ST3 is at Research Road and Thomas B. Landers Road. It's up here at this intersection. And then ST4 is at 30 Durham Road over here. Oops, I'm going the wrong way. Now, this is a very messy looking graph, and I'll explain it a little bit. I don't expect you to really, see what the data are and what they, represent. But I wanted to, I think this is a way to think about all the data we collected and how we used it. And that's what it's here for. So what this is there are two plots. There's a blue plot and a green plot. And then this other thing that's beige is a timing thing. I'll tell you about that. The blue plot is the L90 sound level every 10 minutes. This horizontal axis is time and date, and it's the entire measurement period for 10 days. So this is the 10-minute L90 recorded for the entire 10-day period at Mr. Anderson's house, LT1. And the wind speed is shown at the hub here in meters per second by the green curve. So it's this kind of information that allowed us to sort of see, well, what's the wind like? How does the noise relate to the wind speed? And the beige curve represents when the turbine was turned on and when it was turned off. So when it's at the bottom, the turbine was off. When it's at the top, the turbine was on. So with all of this information, we were able to then take every single 10-minute period and categorize it by whether the turbine was on or off, what the wind speed was, what the sound level was, and of course time of day, which was critical to our analysis. Speaking of time of day, we were tasked to not only determine the worst case scenario, but also the typical daytime condition. There have been concerns about the sound during the daytime as well as at night. And so we took a careful look at the data, and what we found was, if you actually can look at maybe some of these curves, you can see that during this night and this night and this night, when the turbine was turned off, you can see the sound levels drop down here below this 30 line, this 30 decibel, 30 dBA line. And they go down below it, down to maybe 27, 28. And then you'll see the turbine is turned off during this period, and so there's no turbine noise source. And you'll also see that it's only really after midnight and before about 3 a.m. that these reach the lowest. So we found out by listening to our wave recordings that the birds wake in this period of time between June 18th and June 28th, the birds woke up right around 3:30, 3:40 in the morning. And they would chirp and have a nice time. And that affects the A-weighted sound level because bird chirping is kind of like babies, and the A-weighted curve is very sensitive in that range. And so that would increase the sound levels really quite rapidly. And you can see they come right up here before 6 in the morning. Then, of course, you have human activity after about 4:35, and you've got traffic noise. So the daytime sound levels are considerably higher than the nighttime sound levels due to traffic noise and other human activity, as well as birds. So we needed to pick up a period of daytime activity that we thought would be representative of what might concern people, and then a nighttime period which we thought would represent a worst-case condition for evaluating turbine sound impact and compliance with Mass DEP requirements, because they would look at the quietest periods to see what noise impact might be. So this graph, or this table, summarizes what we found with the median L90 values that we measured with both turbine on and turbine off. And I'll tell you that we looked at the reason we looked at the L90 with the turbine on and the turbine off is because it was really necessary to do it that way for comparing apples and apples. If the L90 with the turbine on and is higher than the L90 with the turbine off, then that's related to the turbine. It's clear. The L90 represents the background sound levels, but since wind turbine sound is very steady, even if you look at it in a fast-moving environment, it's very steady. And we were using a slow response meter, so it definitely picks up, all of the noise from the turbine pretty much all the time. And so, if the background comes up with the turbine on, then it's related to the turbine. It's very clear. So that was an approach, and that has proven to be a very effective approach of really knowing when the turbine is dominating the sound level, even when you're not there. So we're not there listening in the middle of the night. We've got these data, and it's very clear that it's what's related to the turbine and what's not by comparing the L90s. Now, the date, if we look at the, well, speaking of the middle of the night, let's look at what the nighttime results were. Between 12 midnight and 3 a.m. at LT1, we end up with a average sound level here. It's not an average, it's a median L90 value and the median hub speed. So median value is half are louder and half are quieter. Was about 37 decibels with the turbine running, and then with the turbine shut down, we had about 29. So, as you can see, an 8 decibel difference. And we attribute that to the sound of the turbine, 8 decibels. And this is a lot of data points. This is 108 in parentheses represents the number of 10-minute periods that were used to determine this value. And we had 54 10-minute periods to help us determine that value. So there's a good solid number of data points behind each one of these numbers. Over at LT2 on Ambleside Drive, we saw a difference of about 4 decibels. And I think it's worth pointing out here that we have the wind speed also indicated. This is the median hub wind speed for all of these data points. And it was 8 meters per second with the turbine running, but only 4 with the turbine shut down. So we see this as, perhaps the sound levels are slightly exaggerated with the turbine running because we had a higher wind speed. Now, if we look at the daytime period, between 7 a.m. and 6 p.m., to us that seemed like a rational daytime period to choose. We see sound levels with turbine running here at LT1 of 43 and about 41.5 at turbine shutdown for a difference of about 1.5 decibels. Doesn't really show much. And the reason is because there's just a lot of background sound. And this is, remember, these are the L90s. These are the quiet periods. In each 10-minute period, you're looking at, only 1/10 of that, 1 minute, only for 1 minute during the 10-minute period was it quieter than that. And similarly at LT2, we only had a 1 decibel difference between turbine running and turbine not running. For these data, we ended up with similar wind speeds for the 2 time periods. So this is a lot of information, a lot of data points in one slide. You recall that I talked about how the wind speed affects the sound level, both in the summary slide at the beginning, the key findings slide. The background sound level is related to wind speed because the higher the wind speed, the higher the wind in the trees, the turbulence created by the wind in the general environment, wind around structures, wind in the trees. And so that increases the background sound. I mean, you can hear it anytime you go out and the wind's blowing, you can hear the sound of the wind. The overall A-weighted sound level increases gradually with wind speed up to, it can get pretty loud when the wind blows. These 4 points down here are points that we measured during periods with the turbine shut down. These are nighttime background L90s, so there shouldn't be much other than wind in the trees noise. There was really nothing else going on. People were sleeping, and so were the birds. And so from a hub wind speed of 4 meters per second up to about 8 meters per second, we ended up with background sound levels from about 28 up to about 33, 32. Now, in order to to do our study properly, we really needed to understand how much background sound would occur at higher wind speeds, because we just didn't have much that kind of high wind speeds, particularly with the turbine off in June. So we needed to understand what it would be. So we looked at the notice report that Epsilon had prepared, and they had conducted those measurements in January in the same neighborhood. And as I mentioned before, their low wind speed numbers were very much like ours, very similar. So we felt that, and they were also able to measure higher wind speeds than we were. So we thought that the data points that they had at the higher wind speeds would be reasonable for us to use for our assessment. And so these 2 points there are points from their data. Now, I'd like to talk a little bit about the frequency characteristics of the turbine sound. I showed you that piano graph, and here's your middle C here around 250 hertz. Here are the babies crying over here at 2 to 4 kilohertz. And here's the very low frequency, at 31 and 16. Now these are octave bands, and so that's why the frequency is doubling each time. And what these show is the average octave band L90 sound levels at LT1 between midnight and 3 a.m., basically the average of all of those data points in each band. And what I did was I took June 20th with the turbine running, which had an average wind speed of about 8 meters per second. And I took June 25 when the turbine was shut down. And during that time, the average wind speed was about 7 meters per second. So we had similar wind speeds up there at the turbine. And these are all the L90s. And what we see is a very clear, effect of the wind turbine at Mr. Anderson's property. It's about, you can see the difference here. This is 40 decibels, this is 30 decibels. You can see the differences, somewhere between, 7 maybe and 10 in these lower and middle frequencies. It drops towards the high frequencies. And so that was one conclusion, which we clearly see that in our data are showing the effect of the wind turbine this way. Also, we noticed that the curve is sort of monotonically decreasing here. This is controlled by the wind turbine. We don't see any peaks in it. And what that tells us is that there's no pure tone condition. The Mass DEP would assess a pure tone condition if we had a peak. If this one here rose up to this value at 45 and then came back down again, that would be pretty close to a pure tone condition, and that would be something that would be considered a violation of their policy. Now, my next slide, I'm going to get into some issues with regard to low-frequency sound. And what I'm going to compare here is I'm going to show you 2 graphs, and these are both in the report, and with an explanation behind them. It's probably a little bit more detailed than what I'm giving you, but so if you want to refer to the report to understand it better, afterwards you should feel free. But what I'm going to try to explain is the daytime effect of the higher sound levels and the higher wind speeds of the turbine. We happen to have our instruments running during a period that we understand that the Andersons were describing the sound as pulses, powerful pulses of sound. And this was a period of time in the afternoon on June 24th between 4 and 5 p.m. And what we had the opportunity to do was to shut the turbine off about a half an hour after this was reported to us. And so we then took the data from those 2 periods, the off and the on period, which were back to back, and the wind speed stayed pretty similar. They dropped a little bit during the off period, but not much. And we are showing you here the 10-minute L90s in octave bands. So again, these frequencies. And the interesting thing to see here is that in the middle and upper frequencies, the curves pretty much overlap. We don't really see much difference. So the turbine isn't really audible. The difference in the sound isn't really audible except in the lower frequency region, and we can see it here. And so that's why, it's been described as low-frequency pulses, because it's that's the only component that you hear, because what's happening here is we have traffic noise and we have background sound from wind in the trees. It's masking, covering up the sound of the wind turbine, making it not distinguishable. Now, there has been a lot of talk about infrasound and low-frequency sound, and I just want to put some solid facts in front of you with regard to that. This graph is also in our report. And what we've done here is we've taken only the very lowest frequencies, and we've looked at 1/3 octave bands rather than whole octave bands. So we have the very low frequency here of 12.5 hertz all the way up to 80 hertz in here. And first of all, I want to show you the sound of the turbine operating and the turbine not operating are shown by these dashed and solid lines coming across here. This is the turbine noise, or the background noise. Now, remember those curves I just showed you with the turbine on and the turbine off for those 20 half-hour periods. Well, these are the same curves, only just looking at 1/3 octave bands down in the very lowest frequency region. Okay? So, and the difference is that we've shown not only L90s, which are shown in these solid lines, this is the L90 with the solid, with the turbine off, and then this blue one is the L90 with the turbine on. And you can see these are 10 decibel divisions here. So you can see that there's that, 8 to 10 decibel increase associated with the turbine sound in the L90s. I also happen to show you the LEQ values, the energy average values, that are shown here in the dashed lines. And they're a little higher because the LEQ is a little higher than the L90, but the differences are about the same or maybe a little bit smaller. Now, I want to show you the two curves shown in green and blue here, which represent the human audibility threshold of hearing, and what can be heard and what cannot be heard with the human ear. The blue curve represents the average audibility threshold, and the green curve represents the average audibility threshold, and the blue curve represents the audibility threshold minus 5 decibels to kind of account for somebody with especially sensitive hearing. So we might subtract 5 decibels if we thought somebody might have very sensitive hearing compared to the average person. But even with a person with sensitive hearing, what we find is that once you get to this frequency range here of about 31.5 hertz, the sound from the turbine here, shown in the dashed blue line and the dashed, in the diamonds. You see it's below the audibility threshold curve. So this 25 hertz, 20 hertz, 16 hertz, 12 hertz isn't audible to the human ear. One thing, though, that sometimes people can hear that relates to vibration, low-frequency sound or vibration, is they can hear windows rattle, or they can hear dishes rattling on the walls. And they might not be able to hear the sound itself directly, but they feel that they're hearing it because they have these manifestations in their homes. We see this in rapid transit systems where the train goes by and it's a very low frequency sound. It may not actually be perceptible, the sound may not be perceptible to the ear, but it might be heard as airborne. And so what we've shown you are the curves of perceptible floor vibration. Can you feel the floor move? Can you feel the wall move? Wall vibration would be the middle curve, and the lowest curve is perceptible window vibration. So you can see that the window vibration is the most, the most sensitive one, the lowest one, and down in this very low frequency range, there might be some detectability at the very low frequencies associated with some window vibration, but again, it's not audible, and it's just tentative there. So that's a bit of some information on low frequency sound. Now, we were asked to see if we could do some reference measurements to determine whether or not this turbine was operating within its manufacturer's spec. So we took our best shot at that, and we followed to the best extent possible the IEC standard that is used for measuring wind turbines. And we measured downwind the way you're supposed to, and we used our ground plane microphone. That's what that is. You see a piece of plywood 1 meter in diameter with a half windscreen over the microphone placed on the ground. And that's the best way to conduct measurements of wind turbines, because you put the microphone up in the air, it's too windy, you get wind noise in the microphone. So this is a tried and true method. You've got to make a correction for the fact that you've got a ground-mounted microphone, but that's all in the standard. So here's what we got. We got, these are our data points down here at different wind speeds of 2 to 8 meters per second for the low wind speeds. This curve here is the manufacturer's A-weighted sound level curve. Now, this is a confusing scale. This is called the sound power level. And the sound power level is a way of thinking about how much total sound power does the wind turbine generate. It's kind of like horsepower, if you will, for an engine. You know, it doesn't tell you how fast you're going to go. It tells you how much power you got. And so that's what sound power level is. It's the same general idea. It's something that you can then convert to sound pressure level to determine what the sound level might be at a distance. So turbine manufacturers are required to specify their turbines in sound power level as a function of wind speed. And here's the wind speed, and this is their curve. So it goes from 101 up to 103 was the highest point we got here for 11 meters per second at the hub. And you will see our data points. We have some blue data points up here for higher wind speeds, and we have these other curve points there. So our conclusion here is that the turbine is operating either about at or about below the manufacturer's specification, because we know that the turbine sound level continues to increase beyond here at about this rate. And I'll show you that in a minute. So we think that we determined that the turbine is at least, about what it should be. It's not an excessively loud machine. It's defective in some way. Now, what is this reference sound power level? Well, these are the numbers that we are given in frequency bands. We need the frequency bands because we're going to do some modeling. And we're going to be modeling how much noise this turbine makes in the community. And how sound travels really depends on the characteristics of the ground, depends on a lot of factors. And so it's important to know what the frequencies are. The air absorbs sound much more effectively at higher frequencies than it does at lower frequencies. Humid air, for example. So our model breaks the sound into all these frequencies to do the calculations, and then puts it all back together once it gets to the receiver location where it's calculating the sound level to determine what the total A-weighted sound level is. So we need to use these reference sound levels as a starting point for the sound created by the turbine itself. And this is the reference level of the Vestas 1.65 at 8 meters per second wind speed at a 10 meter height. This is the highest speed for which we had these octave band frequency information. So we used the highest speed that we had available to us. And this is the reference speed provided by the turbine manufacturer. And they're required to specify the wind speed at a 10 meter height by the specification. Now, before we consider the background sound, we wanted to look at the turbine-only sound from Wind 1 by itself and also Wind 1 and Wind 2 together in the community, and compare that to Falmouth's 40 decibel ordinance bylaw or limit. So what we did was we used our noise modeling software, and I'll show you some noise map contours here shortly. But We used our noise modeling software to predict, to calculate the sound levels at all of these measurement locations, and we compared that to our measurements to see how well our model was working. And it worked very well. We were very close, within less than a decibel under most conditions. Now, you will see that with Wind 1 operating alone, we found that the 40 decibels was not exceeded. Well, we got close at LT1, but was not exceeded. But we did exceed 40 at a couple of locations here with Wind 1 and Wind 2 operating. So we realized that, and that's our calculated sound level. Well, one thing I meant to mention is that these sound power levels that I showed you in the previous slide, these reference levels, they're all based on LEQ. They're all energy average sound levels. This is what manufacturers are required to provide to those of us who are doing permitting noise predictions for wind turbines. It's the energy averages. That's what they can measure. That's what they can calculate. All right, so we skip ahead now to my noise contour maps that I generated, and those are in the report. This is the first one for Wind 1 all by itself. And what we see are, these are contours for the reference speed, 8 meters per second. 8 meters per second at a 10 meter height translates about to 11 meters per second at the turbine, at the hub height. And you'll see that this 40 decibel contour here comes around, it just kind of touches Blacksmith Shop Road here at the property line at the south. It's just a little short of Route 28 here on the west. It doesn't approach the other measurement sites there. And then if we look at the contour map for Wind 2 and Wind 1 together, you can see that it does go across Blacksmith Shop Road, goes over here to LT1 a little bit, and it crosses over Route 28 with Wind 2 now operating, and you can see LT2 is over the 40 contour. ST2 is close to. So that's what we calculated for the wind turbine sound all by itself. Now, in order to assess impact with regard to the Massachusetts Department of Environmental Protection's policy, you need to add the background sound to the wind turbine sound, because it's the increase that they're looking at that they don't want to see. The 10 decibels is an increase from the background L90 to the sound level with the turbine operating. So for the purposes of our assessment, what we had to work with was the turbine LEQ. So we took the turbine LEQ, the energy average sound level, which is higher than the L90 would be, and a little bit, not much, and we compared it to the background sound level. So we add the turbine LEQ plus the background, and we compare it to the background. So, for example, here with Wind 1 by itself, our calculated value for now let me point out, these are nighttime sound levels. No, they are not. No, they're not. These are daytime sound levels. Let's cross that out on your slide. That's my mistake. These are daytime. Wait a minute. No, I'm wrong. They're nighttime with higher wind speed. That's what they are. Yeah, that's right. Sorry, confused myself for a second here. No, that's right. Nighttime with the higher wind speed, and what we see is a wind speed of 8 meters per second, 11 meters per second at the hub. Now that translates to a nighttime background sound level, L90, of about 37.5. And where we got that number was from that curve that I showed you before, where we have the background sound level as a function of wind speed. And this is a relatively high wind speed. So the background sound level comes up to that 37.5. That's where that curve that I showed you intercepts the 11 meters per second. add that to the wind turbine sound that I showed you on this previous slide, using decibel addition, which is a little bit tricky. Decibel addition is where you add 40 plus 40 and you get 43. So this is where 1 plus 1 equals 4. It's an odd kind of arithmetic, but it's decibel arithmetic. What you do find, though, is that if you add 30 plus 40, you only get an increase of about a half, so onto the 40. So 30 plus 40 would give you about 40 and a half. Here we have 37 and a half plus the 40, plus the turbine sound gives you 41. And if you look at the increase, that increase is 3.9 decibels at Blacksmith Shop Road. We see the same trend throughout the rest of the sites with both Wind 1 and Wind 2, with a background sound level of 37 and a half. With this higher wind speed, we see that there are no exceedances, really much more than about 5 decibels above the background. So at the high wind speeds, we don't increase the A-weighted sound level very significantly, even in the middle of the night, in spite of what I said before about the nighttime. And here's the kind of curve that shows how this works. Remember, I showed you this earlier. This is the background increasing as a function of wind speed. Here's the wind speed increasing at the bottom, the A-weighted sound level. And here's the wind turbine sound, just by itself. So we're adding these values together to get the new sound level wind turbine with background. And you'll see that once we get up to the higher wind speeds, the background and the wind turbine sound are about the same, A-weighted sound level. So we're not going to see a big increase in background at the higher wind speeds. But down here, where the wind speed is low, at the hub 6 meters and 4 meters per second, we have the greatest potential for noise impact, where we have very quiet backgrounds because there's not much wind at the ground. It's calm basically at the ground because the wind up aloft is just not that high. But it's high enough to turn the turbine, which has a cut-in speed of 3 meters per second, and the turbine creates this noise here. So while we don't have large increases in sound level at the higher wind speeds, at these lower wind speeds, this is where we see the potential for violations of the Mass DEP policy. So we looked at lower wind speeds. And so this is a assessment at a 6 meter per second hub wind speed, which if you look back at these curves, that's going to be the worst case. 6 meters per second. This is just as low as this value here, but this is a little bit higher. So we're looking at this difference there. And we took the nighttime background, was pretty much the same at LT1 and LT2. The area is pretty homogeneous. It's a quiet area. If there's no cars, then L90 is the quietest periods, and there's no traffic, there's very little wind, it's just quiet. And so this is what we got for background. We add that to the turbine sound, and what we found with wind turbine alone, with wind turbine 1 alone, wind 1, we got increases up to 8.5 decibels at 211 Blacksmith Shop Road. And then if we add wind 1 plus wind 2 together, we see that, well, we got very close to 10, but we didn't exceed 10. And the limit of the Mass DEP says that a greater than 10 decibel increase is considered to be an exceedance. So our calculation ended up with this, so we put it in the report. So it's not 10, but it's very close. It's effectively 10, but it doesn't exceed 10, I guess would be the point to make. The other values, though, close to 10. ST2 on Ridgeview Street, close to 10. Blacksmith Shop Road, close to 10. But not technically a violation there. However, these sites don't represent all the homes, and there are some homes that are a little bit closer at LT2 than LT2 on Ambleside Drive. You may remember from my contour map previously, here, LT2 is not the closest home. There's a couple of them that are a little bit closer. And so with Wind 2 running, we actually do have a couple homes that are above the 10. So our conclusion is that under these kinds of, well, I'll tell you the conclusions later, I guess, but our conclusion is that we have the potential for exceedances in a few homes in the nighttime under conditions with low wind speeds, but we don't see it at the higher wind speeds. Now, I'm going to get off my, what time is it? It's getting late. I'll finish this up very quickly. Noise control engineering conducted their own measurements during my study, and they used a different methodology than we used. We used a slow response methodology. They used a fast response methodology, which is not part of what the standard is, but it's a way for them to see how the sound levels change quickly with time. And they did some measurements at 211 Blacksmith Shop Road and showed some occasional periodic fluctuation of the sound waves, sound levels, which is now often called amplitude modulation. It's basically the swish, swish, swish about once per second. This is the sounds the turbine makes. The sound level goes up and down, and that has a characteristic signature to it. And the his results were presented to the town at the same meeting as mine, and I imagine you'll have an opportunity to see his graphs when he appears before you. My reading of his data show that the magnitude is up to about 4 dBA in the overall broadband, and somewhat more in the narrow frequency bands. He looked at 500 hertz and 315 hertz and saw some slightly bigger changes, about once per second. Okay, Mass DEP was called in to do their own compliance assessment. They reviewed our report. They said, well, Mr. Menge, why have you used L90 and L90? You should be using Lmax and L90. And I said, well, it's not practical to do that with a wind turbine project because you can't know what the Lmax is associated with. Well, long story short, they insisted on, they asked us to look at our data a couple different ways. We did that for them. Then they thought, let's go out ourselves and see if we can use our sampling method that the Southeastern District of the DEP has used for a while, and which is to look for maximum sound levels and to use their ears and determine when the turbine is controlling the sound and when it is not, and choose those time periods that as representative of the turbine sound, and compare that to the background L90. Their measurements are periods of about 5 minutes times 3, so maybe 15 minutes. Anyway, so they conducted a series of measurements. It took them quite a while to get 4 nights where they could get some data, but they did it. And they got one site, and just one site, that showed exceedances of their policy. And they were slightly above the Mass DEP's 10 dBA limit. And the way they did it was by comparing the maximum sound level that the turbine made in 3 separate 5-minute periods to the L90 with the turbine not operating. Now I had some concerns about not only their methodology but their findings for these analyses. And my concern about their findings for these analyses were that the wind speeds at the turbine hub were higher during the measurements that they made with the turbine running than they were during the ambient measurements to which they were compared. And I thought that was, it's not quite right because we know that the background sound level increases with increasing wind speed. And second, this is an issue that we have had with Mass DEP and particularly the southeastern region using the Lmax as a metric for turbine sound level. It's not specified in their policy guideline. It's not consistent with the LEQ metric, which is the only thing that's available to manufacturers and to us consultants to determine how much noise a wind turbine will make, because it's what's used for, it's what the manufacturers provide, so it's what we must use for permitting. And it's not been consistently used in other DEP districts across Massachusetts. Other concerns that I have with their methodologies, their time periods are very short, not sufficient to establish a truly stable sound level. They can't measure a lot of different conditions. They can't necessarily match the wind speeds the way they should. And it's very subjective. That's another problem with it. The observer must listen and decide whether the sound is dominated by the turbine or not. And to be honest, the sound of the turbine is wind turbulence sound over the blades, which is similar to the sound from wind turbulence from interacting with other structures, such as trees and houses. So the character is quite similar. The frequency spectrum shape is quite similar, and it's difficult to do this kind of subjective testing. And their methodology, I'll give you this final one. The Mass DEP convened a wind and noise technical advisory group in 2013 to address problems with their current compliance methods for wind turbines because they realized they had issues with it. And there were many criticisms of the current methodology. I'm not the only one who feels that it's an issue. They reported daytime measurements as well. I just gave you the nighttime results. And they found that for the daytime measurements, they got no exceedances of the Mass DEP's 10 dBA increased guideline and no pure tone condition. Finally, I wanted to just comment briefly on a report that I received prior to this meeting, prepared earlier this year by Noise Control Engineering, some infrasound measurements conducted inside the home at 211 Blacksmith Shop Road. It's a very low frequency sound and conducted with the turbine running and with it shut down. They conducted on 4 occasions with special infrasonic instruments, and they did some narrow band spectral analysis, which is down to fractions of a hertz, and they found that you can see little peaks in the sound spectrum at the turbine's blade passage frequency of approximately 1 hertz. Well, my comment on this, I have a couple. One is that while this once per second swishing of the turbine blades can be heard as audible sound in middle frequencies, that is not inaudible infrasound. The 1 hertz to 5 hertz tones that are shown in these graphs are way below the threshold of human hearing and aren't perceptible as sound. Medical expert panels have repeatedly asserted that low levels of infrasound are harmless. And at the end of his report, he says that the turbines are acoustically trespassing. And that's a term that I've not seen before in my 40 plus years. Finally, I just mention that we all have, many of us have very sensitive instruments that we can use to measure a lot of different things. And you may have seen images of seismographs measuring, the vibration of the ground, and then when an earthquake comes, you see it peaking up. And I think this is something similar. We're measuring imperceptible things that you can perceive, but when the ground is moving, the seismometer can detect things that the people aren't able to. So finally, I have a conclusion slide here. I don't believe that wind 1 is expected to produce noise levels greater than the town's 40 dBA limit at the nearest residential property lines. So from a wind 1 standpoint, I think it's in compliance with the town. With both turbines running, the 40 may be exceeded at a few of the nearest homes at the higher wind speeds, but background sound levels at that point are approaching or exceeding the turbine sound levels, and you can't really be sure what's the primary source of the sound in many cases. Now, with regard to the DEP criteria, the wind 1 and wind 2 are expected to increase quietest nighttime broadband sound levels by no more than 10 decibels, the Mass DEP criteria, operating individually. But with both turbines running, we see increases in background could be exceeding 10 decibels at a few of the closest homes late at night under these low wind conditions, like I mentioned before. So we're thinking that potential conditions to permit might be to avoid potential exceedances of the policy, would be to require that during the quietest early morning hours, one of the two turbines could be curtailed with increased cutting speed up to 8 meters per second, such that that you would have to have a higher wind speed, which would create the higher background, and it would not give you such a substantial increase to avoid the exceedance increase of greater than 10 decibels. And our calculations show that it could be either wind 1 or wind 2 could be used for this, because it's the combination of the two that causes the exceedance. So that's all I have.
Thank you. How do you think we should proceed?
Well, I think personally I'd like to ask a few questions
Okay.
while it's fresh in my mind.
Okay. I'm on board. Ken, why don't you get us started then?
So I'm just wondering, in light of the particular wind speeds that you measured, is there information on the average wind speeds in these locations?
Over long periods of time,
Yes, over an annual.
I
I mean, what proportion of the time would we expect the wind speed of 8 meters per second, 10 meters per second, so 3 meters per second, et cetera?
I don't have that at my fingertips.
Not at the fingertips, because what we do have.
If you're going to speak, you'll have to come up and just identify yourself for the record.
And relevant to that also
Data
is...
exists, data exists, but I don't.
I'm don't doubt that data exists somewhere.
Yeah.
Just factoring that into your model might allow a kind of a broader perspective in terms of how much of the time we can expect exceedances. And you didn't address at all wind direction and whether that makes any difference to, you know, the noise levels encountered at these various homes. You only talked about speed.
I did. And I think maybe I missed an opportunity to clarify things. The reference sound power levels that we used in our modeling are based on downwind conditions, which is the worst case direction for measuring sound levels from wind turbines. So that downwind sound level is radiated in all directions to create our noise contours. So it's basically a worst case contour set. So the exceedance is likely to occur under downwind conditions, not as likely to occur under crosswind or upwind conditions. However, I will also say that wind turbines at these distances are not extremely directional. You may get a 5 decibel shift at these distances, but it's not going to be 15 or 20.
And then I'm wondering if you're modeling, because I noticed it was somewhat irregular, does that take into account landform?
Yes.
And how does it take into account landform?
Well, we use a digital terrain model, and we incorporate and we bring that digital terrain model, which shows all the terrain, into our computer program, so it knows where there are earth burnt, where there are buildings, and we had some buildings in the model too, the larger buildings, but it's mostly terrain that reflects this. We did not have trees turned on. We did not include any leaves on trees in the sound propagation because we wanted to reflect worst case kind of wintertime conditions. That's another thing I could mention.
So no trees, downwind,
Mm-hmm.
and just addressing that landform issue a little more, you know, how does it work if there's a valley, for example, that might, is it possible that some of this sound can be essentially funneled to a locus and concentrated there so that it seems louder in a particular location than it might, you know, at the same distance from the source but perhaps on a ridge or in a flat area?
It's conceivable. Certainly, sound reflects from the ground. Sound reflects from buildings. So, for example, if you were to have a building in a corner, and you had a window in that corner, and the turbine was facing that window corner, you would have some amplification of the sound because you had a reflection from this surface and a reflection from that surface. So there are certain effects that buildings and terrain to some extent can affect sound. Yeah, definitely.
And so you made some measurements at 211, which you said was Neil's house?
Yes.
Mr. Anderson's house. Was that inside the house, at the driveway, at the top of the street? Exactly where was that located?
It was all outside the house. It was fairly near the street. It was kind of, I think, at the edge of his upper parking lot area. We didn't put it down at the house itself. We don't generally measure sounds inside houses. I mean, it's very tricky because there's interior equipment that makes sound, and plus the outside to inside noise reduction of a house is a lot. I mean, sound levels will drop by 20 decibels or 25 with windows closed, and less than that with windows open. But so it's outdoors where we generally always have to conduct our measurements.
And are those drops in noise level, are they uniform across all frequencies?
No, they're not. They're not. It'll drop more at higher frequencies and less at lower frequencies.
But there would be an expected drop at a lower frequency.
Oh, yeah.
And you would expect the presence of foliage to decrease the noise levels? Is that
Slightly. Not much.
okay?
It's a small effect, but it's an effect that we don't need to confound the issue with, so we leave it out.
So in this range of about 40 decibels, what would be the, could I detect a difference between 40 and 41?
No. Not by itself, unless you had some headphones on and you were listening very intently and somebody played you back and forth 40, 41, 40, 41, you could probably tell the difference.
So what would be the minimum that an average person might detect a difference?
They say it's around 2 or 3. In a community setting, generally the criteria we use is 5. For example, that's generally one of the reasons you see my contours in 5 decibel steps is that's generally the way that, like for example, Federal Aviation Administration, they have their 5 decibel steps for determining noise around airports, and you know you're within one zone or another zone at between 60 or 65. Also, the 5 decibels has become very commonly referred to as the sort of the threshold of noticeability community-wide. Federal Highway Administration, for example, won't fund noise abatement unless it provides a 5 decibel reduction. They figure that the community won't notice it unless it's 5 decibels or more.
Okay.
Okay. TJ?
Thinking myself.
Okay. Ed?
Yeah, was there any recordings made of the wind direction?
Yes,
So that's available?
yes, we have that.
That's all I have.
And you can provide that to us, or have you provided that to us already?
It's probably posted in the data set that's on the town's website, but from the spreadsheets that we provided years ago. But I can check on that. I'll have to check with my colleagues to make sure we provided wind direction as well.
Okay, because we make the decision based on the information that's in our files, so it needs to be submitted to us.
Oh, okay, so you won't have that right now, no.
Okay.
But I could get it for you if
Okay.
you wanted it.
Thank you.
That's all.
That's all? Paul?
No questions, thanks.
Okay. Let's see. Does time of year, and I think that there's been some testimony anyways that time of year may play a role, and that might have to do with the prevailing winds, but you said that you started your study in May to June, would you expect to see different results in a different time of year?
Well, sure. If we were into cricket season, which generally starts sometime in July, runs through October, we would have noticeably higher background sound levels at night. Now, having said that, those are all in the high frequencies. They're all at 2 kilohertz, 2,000, 4,000 hertz. So that isn't going to really have a big effect on the covering up wind turbine sound, the way wind in the trees will. So, but that is an issue. So one has to think about, what do we do about insect sound? Or tree frogs in the spring. We run into tree frogs in the spring, peepers. They make a lot of noise, and your A-weighted sound levels go way up. That needs to be corrected for, adjusted for, or avoided in order to really do a proper assessment of wind turbine impact on a community.
Okay.
Other times of year, the wind direction, prevailing winds, higher winds often in the winter and the fall. Leaves on the trees will affect background sound somewhat. You get rustling of leaves if you've got higher winds, maybe a little bit more in the summer than you would have in the winter. On the other hand, we did see very similar results between our measurements in June and the measurements that Epsilon conducted for NOTIS in January. So there wasn't much difference.
Okay. Aside from mass, I know that the NCE infrasound measurements, so that's a little bit different of a measurement, it's my understanding. And then the mass DEP measurements of Win 1 and Win 2 for compliance with DEP's noise policy. Aside from those, which I think you've said there were some flaws in their testing, that's your opinion, has there been any other study of Win 1 and Win 2 operating together in the real world? Because I know that you use modeling, but has there been a study of both?
I don't believe so.
Okay.
I could be wrong. I haven't stayed as connected to this as some have.
But not that you've reviewed?
No,
at
not
least.
that I've reviewed, no.
Okay. I just want to go through my notes, see, I've written down some questions. Some of them were answered already. What is the effect, well, you say Mass DEP's, it's a noise policy, so it's not their regulations, it's a policy they've adopted?
Yes,
Okay, and so have we been provided that full policy too?
it's in the report.
Okay. What is the effect of violating Mass DEP's policy?
Well, they work through boards of health, local boards of health.
Okay,
And so it's up to the local board of health to take action. And if they determine there's a violation of the policy, the local board of health has the ability to make changes, recommend abatement measures, or in the case of curtailment measures. So it would, Mass DEP does have the force of their policy, and it's backed by a Massachusetts air pollution statute,
okay,
and that's referenced in the report.
okay, thank you.
Yep.
I think that's all I have for right now, too. Any questions? Yes, you all set? Okay, I think at this point, we are after 9:30, which is usually where we like to end for the night.
I just spoke with Attorney Tillotson, and I
Yes.
asked whether the gentleman might be available at a subsequent meeting, because there may be questions that Attorney Senni wants to ask, and I'm sure the audience may have a few as well.
Yes.
And she indicated that that was a possibility. I'll let the two of you explore that.
Okay.
That would be great.
We can discuss that if the board, certainly if the board thinks it would be helpful.
I think that probably would be helpful because we've obviously heard a lot tonight. We've been here since 6, which was earlier than we usually are. So I think it would probably be a good time to kind of break on this.
Yeah, and I think the audience and Mr. Senni deserve a chance to ask questions.
Right, and not a rush chance, so, absolutely. Okay, so,
You have a question back there.
question, sir, if you're gonna ask a question, please stand up, but nothing substantive, I
The
hope.
uninitiated, I'd just like to have.
If you need to provide your name, and nothing substantive. I'll let you ask a question about what our plans are as to.
Could I have a interpretation as to, I should say, a clarification?
Excuse me, you need to provide your name and your address for the record, sir.
Richard Bowen, 106 Ambleside.
Thank you.
I'd like to have and really to find out what the translation is between 11 meters per second and miles per hour.
Sir, that's a substantive question. So that's something that we're going to take everybody's public comment at the next hearing. So.
It's not a comment. It's just
Well, I understand, but any questions or public comment, just for the fairness of everybody present. Substantive questions will be handled at the next hearing. Thank you. Okay, so does anybody want to have a motion to continue?
Motion to continue.
Seconded.
Okay, and that's, we need a date.
Time and date, sir.
So I believe it was December 10th, is that what everybody had?
Can I ask a question first? Chris, you have somebody speaking December 10th? Because we do have, we'd like to continue it to that date. I'm not so sure if we're going to be able to get,
Excuse me, can we please refrain from public comment? Thank you. Yes, sorry.
to get everything in on the 10th. We'd have 2 other hearings that night. Not big ones, well, one might be. So I'm just not sure if we bring Mr. Mensch back then or.
That's some subsequent.
Correct. Because I know you guys have all talked about Chris Senni having a presentation on the 10th.
Right, and I have another witness as well, but we can discuss whether it makes sense to do that on the 10th or so.
All right, so let's go ahead and continue it.
Well, we're continuing the hearing either way to the 10th.
Right, that's
We'll
what I'm
look at
saying.
it.
I'm just trying
Yeah.
to figure out how
So we
we're going to do that,
Okay.
leaving it up to Diane and the attorneys.
And I guess the other question would be, if you're gonna-
Excuse me, we're discussing.
Oh, I'm sorry.
Thank you.
are you, if we continue it to the 10th, are you going to continue it to 6 or at some time later after your other 2 hearings?
You'll probably want to take it out of,
Order.
right.
I'm fine coming earlier, I just, 6?
Six.
6 is the max.
Yeah, 6 is all right.
6 is commendable.
My only issue is, you would be doing this one, then you'd have to procedurally
Yeah.
stop it to open up the other 2 at 6:30 and then either continue with this one and put those off, or,
Have those been noticed already?
yes, of
For
course.
6:30? Oh, I didn't know, for
Yeah,
2 weeks.
they have to be advertised and abutters notices have gone out.
Okay.
yes.
You don't want to make them.
Yeah. Well, we can start at 6.
Okay, that's fine, it's up to the board. So you want to go ahead with your
Best use of
motion,
time.
excuse
Yeah.
me?
So I believe it was Paul and Ed seconded it
Yes.
for a continuation of 7015.
No,
Oh,
no.
excuse me, 6215, sorry about
Correct.
that, to 6 PM on December 10th. Is that correct? All those in favor?
Aye.
Aye. Okay, unanimous. Thank you.
And we will
Thank
have
you.
recommend-
Madam Chair,
Yes.
Richard Latimer, Precinct 162 Prospect Street. I just have a procedural request. Inasmuch as many of us have been waiting here for several hours to speak, would it be possible just to take a list of those who are here who want to speak, who will be given precedence at the next?
No, sir, it's not.
It won't be possible. Thank you.
Thank you. All right, we have open meeting.
So we're going to continue.
All right.
That's nice.
It is the same. They have other business.
Yeah. Just minutes. And,
All right. We're going to be be continuing with open meeting items, so if you could have conversation in the hall, it would be appreciated.
And then don't lose track of the signatures. So, be in the loop as to when. Wonderful. Thank you very much. Good night, everybody.
Thank you.
You as well. Thank you, Diane.
I was only an hour late, hour and a half.
My estimate was
His Wednesday.
I know. Okay. So the minutes of November 12th, has anybody had a chance to review?
Yep,
Everybody?
I'm good with it.
Okay.
He wasn't here.
No, okay. I'll refrain again because I'm a delinquent board member. So, does anybody have a motion to approve?
Motion to approve the minutes
Second.
of November 12th.
Okay, and Ed
Second
seconded
it.
it. Okay, all those in favor?
Aye.
And I'll
Abstain.
refrain. Oh, I abstain as well.
3-0.
I abstain. Was not here.
I was here, I just don't. Okay. Bylaw review update. I don't think that there's any updates, right?
No.
Correspondence, board updates. Sorry, any?
No.
Future agenda items?
I guess we'll be
You like-
talking about the wind turbines some more.
Yeah. Well,
They're starting to give me a headache.
yeah.
I did, by
No,
the way, I
I'm
did
only
put
kidding.
the bylaw review updates in your meal slots
The updated one.
for people who have been in the office.
Thank you, sir. All right, I
feeling-
suppose that's all.
yeah.
Oh,
Oh, you want?
but do you want to do this or not?
No. I know, sorry.
Policies?
I keep meaning to do it. Have you? No. You trust their changes.
Did you do what we asked?
Yes.
Then I think
And
you
I
should
sent
just
them
say,
out to you
okay.
guys, yes, a long time ago, Ken. Everything that you guys did, and Ashley and
I saw
I
it.
incorporated, we both reviewed everything.
I'm
So you guys
confident.
All right, I'll
just,
vote on it. And then
you guys-
it's fine.
well, if you're not
No,
ready with it, you can do it December 3rd.
No, but I know it keeps getting pushed off. Okay, we'll push it off once more. What could it hurt? Is everybody else all set?
Yeah?
Yep.
Okay.